Recording started as well. It says it's recording. So.
Okay. All right. Sorry. It takes me a while to figure out how technology works, you know?
It's okay. First
Okay.
chunk of the
So,
semester.
yeah, welcome everybody. Thanks for showing up for the first talk in the US friendly time zone here of the One World Mind seminar. Um, we have a Santhosh Karnik, who has been a former organizer of the seminar, who was willing to show up and be the first speaker this semester. He is currently a postdoc at Northeastern University and is transitioning there from Michigan State. Got his PhD at Georgia Tech, working with Mark Davenport, right?
Yep.
And yeah, he's here today to talk to you about tensor completion. So I will turn things over to you, Santhosh.
Okay.
Thanks for talking.
Yep. Thank you to the organizers and Mark for inviting me, and thank you all for being here today. So yeah, and just to mention, this is joint work with collaborators Cullen Haselby, Mark Iwen, who are both in the audience, and Rongrong Wang, who might be here, might not. I'm not sure, but that's good. Okay. So just to give a brief outline of what we want to go over. So like our contribution is methods for completing low CP rank tensors from a subset of observations. And we're providing rigorous theoretical guarantees, at least in the case where there is no noise added to our observations. No one seems to be able to prove things with noisy tensors, so that seems to be a hard problem. So just to give an outline of this talk, we're going to start by reviewing low-rank matrix completion, which will probably be like review for most of you, but there may be one or two people in the audience who haven't seen that before, so I'd like to go over that. Then I'll follow it by a little review of tensors, then review the previous results in low-rank tensor completion, and then talk about our results, followed by some numerical experiments. Okay, so to go over low-rank matrix completion. So again, the problem setup is we suppose we have a matrix that is rank R. For this ease of presentation, I'm assuming I'm going to just have the notation be such that the matrix is square, but everything I'm going to say is going to extend to the case where the matrix is rectangular. It's just less notation needed for ease of presentation, though. If I just assume it's square. Anyway, so suppose this matrix has rank R, and we observe some subset of its entries. So you can think of it as here's the matrix, and these colored blocks are the entries we see. Our goal is to like fill in the missing entries. So in other words, we'll recover the entire matrix from these observations. So this is a pretty popular problem. There's been extensive literature on the subject. I don't have time to go over all of it, but we'll highlight a few results in the area. This application-wise, I think the most popular application is like in recommendation system. So you can think of like each row being a user and each column being like some sort of item. And then like the filled in entries are each user having some rating for that item that they've tried out, maybe a movie they've watched or a product they've purchased, etc. And of course, not every user has purchased or watched every single item in your collection. So you only see a subset of this, and you'd like to be able to say, okay, for each user, which are the next, what items should they like consider buying, or what movies should they consider watching, etc. Where might like the high values in this matrix that I haven't seen be? And so that's why you might want to learn to complete a matrix from missing it, from only partial entries. Okay, so can we recover this matrix from an observations? So the matrix has n squared entries, but it has only something on the order of r times n degrees of freedom. So this seems like it might be possible as long as the number of observations is at least the number of degrees of freedom, but there are some constraints involved. So just to give you some idea of when it's not possible. Well, here's a couple examples. So let's consider this first case here, where we've observed n squared minus n entries. So all the entries in the second through last columns. And we haven't observed any entry in the first column. So unfortunately, there's no way to determine this first column, even though we have most of this matrix, because this first column could be any linear combination of the remaining columns. So again, in general, we need at least 4 entries in each row and column. Otherwise, that entire row or column can't be uniquely determined. So the way most works deal with this is that they observe a uniformly random set of entries. So each entry gets sampled IID with some probability, and that probability is set such that like you are almost certainly going to see at least R entries in each row and column. Okay, and so another edge case. Okay, here we have n squared minus 1 observed entries in this matrix. These n squared minus 1 entries are all zeros, and this one entry is some non-zero thing. So this is a rank 1 matrix. We've observed, which is like the lowest rank possible. It's not trivial. We've observed all but one of the entries, and we still can't recover this missing entry. Of course, this is because, again, we need the sort of like L2 norm, or I guess the Frobenius norm squared energy to be spread out over the matrix. So that way our random observations capture enough of this energy, get enough of this information, and have a chance to recover things. If the energy is highly concentrated, like 1 or even a small number of entries, there's a good chance that we'll fail to capture that, and then we'll be missing a lot of the information needed to recover the matrix. And so the way most works deal with this is that they assume that the row and column space has what's called a low coherence. So effectively, they find the coherence of a subspace as the dimension you're in over the rank, or the dimension of the subspace. And then they look at times the maximum L2 norm squared energy of the projection of a Euclidean basis vector onto that subspace. So if a subspace, let's say your subspace is spanned by f of t vectors, or sorry, discrete Fourier transform vectors, it's going to have coherence 1, for example. And another extreme case is if a subspace has a Euclidean basis vector in it, then the coherence is going to be n over. And so in general, low coherence is better for matrix recovery than higher coherence. Okay, so now question, how do we actually recover the matrix? So the ideal thing to do is say, okay, look, we want to find the matrix X whose rank is as small as possible, subject to the constraint that it matches all of the observations that we've seen. So that's sort of the standard setup that you might think naively, but unfortunately this problem is non-convex and NP-hard. So we can't really solve it. What hasn't been known to be popular is to do what's called a convex relaxation. So the rank is just the number of singular values that are greater than 0. And so like if you think back to like compressed sensing, you might want to think, okay, how many entries are non-zero? That's the L0 pseudonorm, and that gets convexly relaxed to like the L1 norm, which is like the sum of the absolute values of entries. So we can do a similar thing here, where we use what's called the nuclear norm, which is we replace the rank by the nuclear norm, which instead of the number of non-zero singular values is the sum of the singular values. And now we're just trying to minimize the nuclear norm subject to matching all these entries. This problem is convex and it's solvable in polynomial time. So this is a fairly popular method for doing this. Yeah. And so here's one result. Note there are many results in the literature about low-rank matrix completion, but here's one result that's sort of representative and that we'll use later on. So again, if we have an n by n matrix whose row space and column space coherences are bounded by some constant mu naught, and each entry of the matrix is sampled independently with this probability here, some constant times the coherence times R times log squared of n over n. Then with high probability, M is the unique solution to the nuclear norm minimization problem. Okay? So what this means is that with high probability, we'll only need the coherence n or log squared n samples that are taken randomly, and we'll be able to recover the matrix. And in 2010, Candace and Tao showed that this is optimal to within a log factor. Okay, so that was on just low-rank matrix completion in the what's called non-adaptive case, meaning I give you all the samples you're ever going to see, ever going to get from this matrix, And then you have to just go use those samples. You can't see any other samples, don't get any other information, complete the matrix. Now, what if we're allowed to adaptively sample the matrix? That means we can pick a few entries, use that information to decide what the next set of entries to observe, use that information to decide the next set of entries to observe, etc., until we've like exhausted a sample budget, and then we have to complete the matrix. Now, does that adaptive sampling allow us any kind of gain over just getting all the entries at once? And so there's a theorem in Balkan and Zhang's 2016 paper that says essentially there exists an adaptive sampling strategy and a recovery algorithm that if you have an n-by-n matrix whose just column space coherence is bounded by mu naught, then the algorithm will, with high probability, recover the matrix and use less than the coherence times n times r times log of r over delta samples. So what that means is that if you're allowed to observe the entries in an adaptive manner rather than getting them all at once and having to complete the matrix, your sample complexity gets reduced from having this log squared n factor to having this log r factor. So there's a mild but noticeable reduction in the number of samples if you're allowed to sample adaptive. Okay, so now that we've, hopefully that was just a review for most of y'all. Now let's get into tensors. So we're going to start with just order 3. So tensors are or just in general like a d-dimensional array of numbers instead of like a 2-dimensional array of numbers. We're going to start with the order 3 case, meaning that we have a 3-dimensional array of numbers. Again, later on in this talk, we'll talk about order d tensors, but for right now, we'll just stick with order 3 tensors just to like warm up. So, and again, we're going to start with a cube, a tensor that's a cube. So the number of rows and columns and number of cubes, which is what you're calling the third mode of the tensor, are the same. But again, what I'm saying is going to extend to, I guess, rectangular or general size boxes. It's just that we have fewer subscripts and it's easier to notate. Okay, so again, if we have an n by n by n tensor, we're calling it rank 1 if the entries are in the form something that depends on I times something that depends on j times something that depends on k. And again, we can write a rank 1 tensor as the outer product of 3 vectors. Similar to how we can write a rank 1 matrix as the outer product of 2 vectors. The rank 1 tensor is the outer product of 3 vectors. And the CP rank of an n by n by n tensor is the smallest number of rank 1 tensors whose sum is that tensor. So here we have this tensor here that it can be decomposed into R rank 1, the sum of R rank 1 tensors. And so if there's no smaller number of rank 1 tensors that add up to this tensor, then its CP rank is exactly R. Otherwise, this only proves that the CP rank is at most R. So important thing to know. For notational purposes, we'll define factor matrices, which are basically, we define the A factor matrix as stacking all of the first modes vectors into as columns of one matrix. The B factor matrix is stacking all the mode 2 vectors as columns of this matrix, and similarly for the C matrix for the third mode's vectors. Okay. And it's important to note there are many other notions of the rank of a tensor, such as Tucker rank, tensor train rank, etc. But these are defined differently, and we won't get into those. This CP rank is one of the more natural extensions of rank from matrices to tensors that you would think of. Anyway, so CP rank, unfortunately, is one of the more trickier ranks to work with. In Kulda and Bader's popular paper on tensors, they have more details about what I'm about to go over, but here's just a summary of some of the details of why CP rank is a bit challenging. So with matrices, the dimension of the row space, the dimension of the column space, and the rank are all the same. Whereas in tensors, again, this sort of property that holds for matrices doesn't quite hold. The dimension of the row space, the dimension of the column space, the dimension of the tube space, and the rank could all be different different numbers potentially. Let's see. Another property is that they rank over, if you define over the reals, meaning I need to decompose it into like a sum of real rank 1 matrices, is going to be the same as the complex rank for matrices. But with tensors, these might not be, even when your tensor is purely real. You could have, there are examples of tensors that have like CPU rank of 3, and when you restrict it to be a sum of real rank 1 tensors, but then their complex CPU rank is 2. Okay, another property is that the essentially the set of rank deficient matrices always has measure 0. So most n by n matrices are going to have rank n. If you like generate so now formally, if you generate each of the entries IID with like some continuous distribution, let's say Gaussian, I guess, then with probability 1, the rank will be n. Whereas with tensors, this is not true. In fact, you can have the set of ranks for which this set has positive measure, there are multiple values of R for that. And in general, it's not known how many which values of R for a given size n this set has positive measure. Okay. Another challenge is that with the matrix case, computing the rank has order n cubed runtime, whereas with tensors, computing this rank is NP hard. In fact, there exists a tensor with all 0, 1 entries that's only 9 by 9 by 9, so only 729 entries, whose rank is still unknown. And people have been at this one particular tensor for a couple of decades now, and we still don't know what the rank is. Let's see. Another challenge with CPU rank is that for matrices, the truncated singular value decomposition gives an optimal rank or approximation with respect to both the operator norm and the Frobenius norms. So if I have a matrix and I say what's the best rank R matrix to approximate this, all I have to do is take the SVD, set all the last n minus R singular values to 0, and then multiply that out, and I get the best rank R approximation. Whereas with tensors, this property doesn't hold. In fact, you can even have like things like a sequence of rank 2 tensors that converge to a rank 3 tensor. So meaning that, a tensor that has CPU rank 3 can be arbitrarily approximated well by a CPU rank 2 tensor, but there's no single best approximation. And even worse is that these approximations aren't always nested. So in like the matrix case, if I have a rank R, if I have a best rank R plus 1 approximation and remove the last term, I can get a best rank R approximation. Whereas with tensors, these approximations aren't always nested. So greedy approaches, even when you have all the entries, a greedy approach to find the CPU rank generally fails. So yeah, these are just kind of the flavor of things that make working with tensors, in particular the CPU rank, challenging. Okay, so now let's talk about tensor completion, just for the order 3 case. So again, suppose we have this n by n by n tensor whose CPU rank is R. So I know the CPU rank, and I get to observe some of the entries, but not all of them. And my goal is to fill in the missing entries. Okay, so can this be done? So again, this tensor has n cubed entries, but only something on the order of 3nr degrees of freedom. So it seems like this could be doable, but again, some assumptions are needed. So you can ask, under what conditions can we recover this tensor? How many samples do we need? And like, does adaptivity help? Similar to like what we asked in the matrix case. Okay, so some prior results on low CPU rank tensor completion. So most works consider this fairly standard case of non-adaptive and uniformly random sample. So many of these tensor completion works get something on the order of like n to the 3/2 samples, even when the CPU rank is a small constant. And this tilde means that we're suppressing like log factors that could be log to the 300th power or something. But they all have like some n to the 3/2 dependence. Recently, Stefan and Zhu obtained got rid of those log factors and obtained a method to complete n by n by n tensors using n to the 3/2 samples. And this is believed to be pretty close to optimal because it's been shown that recovering an n by n tensor with CP rank R from n to the 3/2 minus epsilon uniformly random samples is as hard as solving a 3-set problem, which the best computer scientists have worked on for decades and haven't figured out how to do that. So this is believed to be NP hard. Yeah, so that's the state of the literature with just non-adaptive and just uniformly random every entry sampled independently with some probability. Okay, so now what about adaptive sampling? So there was Krishnamurthy and Singh that proposed a method which can recover a tensor with high probability and requires something on the order of coherence squared n r to the 5/2 log var samples, where again the mu naught is a bound on the row and column space coherences of the tensor. Again, r is the rank, n is the dimension, and delta is your like failure probability. So by allowing adaptive sampling, we go from needing n to the 3/2 sample down to something linear in n. The cost is that we still have like an r to the 5/2 power and coherence squared dependence. Okay, so now time for our first result. So in the adaptive sampling case, we have a method. So we have our theorem says there exists an adaptive sampling and reconstruction algorithm such that for any CP rank R tensor whose factor matrices satisfy these conditions, the algorithm completes the tensor after observing something on the order of the coherence n or log r over delta entries with high probability. And the conditions are that the first two factor matrices have full column rank. Only the first matrix has a coherence bounded by mu naught. And this third technical kind of intricate condition that says every S by R submatrix, for some S, every S by R submatrix of the third factor matrix has critical rank at least 2. So we are able to improve the dependence on, so just some notes on this. So we're able to improve the dependence on the rank and the coherence. We only need one of the factor matrices to be coherence. The con is that A and B have to have full column rank, and we have this like technical condition on this third factor matrix. However, we note that a random C drawn from a continuous distribution will satisfy this third condition with probability 1. We note that this just means that like for S equals 2, this means if I take 2 rows of C, all those like 2 vectors in those 2 rows are pointed in different directions, which again, if C is random, that happens with probability 1. Of course, real world tensors might not be as cooperative. Okay, so a sketch of our adaptive algorithm, which we call the adaptive tensor sandwich. So step 1 is that we complete S mode 3 slices via an adaptive matrix completion algorithm. So you can imagine like, we pick, let's say the first slice and the last slice here, and then we use some adaptive sampling method to, in a structured way, sample the entries and complete those 2 slices, okay? Then step 2 is we're going to use something called the simultaneous diagonalization algorithm on this completed subtensor. So we have an n by n by S. In this case, S is 2, but in general, it could be something higher. We're going to use this simultaneous diagonalization algorithm to then learn the first 2 factor matrices. Note the simultaneous diagonalization algorithm in the literature is sometimes referred to as Jenrick's algorithm. However, it's been pointed out that Jenrick was not the first person to discover that, and there's quite a bit of controversy on its name. Anyway, so after completing that subtensor and learning the first 2 factor matrices, now we only have one more factor matrix to determine. So now we just have like a linear system of equations to solve for that third factor matrix. So for each mode 3 slice, we can sample our appropriately chosen entries and then solve a linear system of equations to learn one of the rows of C. And then just do that for each of the n slices to get the entire third factor matrix. And of course, once you learn all three factor matrices, that has all the information in the tensor. Okay, so just to outline each of the steps of the proof, for that slice completion step, again, we're going to pick a subset of S indices. For each of those S slices, we're going to use the adaptive sampling method in Belkan and Zhang's 2016 paper to sample and complete that slice. And then for each slice, with their method, we need this many samples. The coherence n are log of r over delta samples, and that recovers it with probability at least 1 minus delta. And so if we do that S times, now we need S times as many samples, and then the failure probability gets multiplied by S because there are S chances for one of these slices completion steps to fail. Okay, so that's the slice completion step. Then we need to, now that we have that completed subtensor, so like this slice and this slice together, we can then use the simultaneous diagonalization algorithm. So what we're going to do is we're going to take two random vectors, x and y, and add up this random linear combination of these completed slices. So tx is we're going to denote this as a linear combination of the S slices that we've completed already. And similarly with ty. With a little bit of algebra, we can show that this tx matrix, that first linear combination, can be written as the first factor matrix times a diagonal matrix times the second factor matrix transpose. And similarly, this other linear combination can also be written as the first factor matrix times a diagonal matrix times the second factor matrix transpose. Okay, so that seems fairly innocuous, but now what can we do with this? Well, the columns of A and B we assumed A and B had rank R. The columns of A and B are linearly independent. So we can compute the first linear combination times the pseudo inverse of the second linear combination. And that gives us the first factor matrix, a diagonal matrix, and the pseudo inverse of the first factor matrix. And then we can do the same thing, but with the linear combination swapped to get the second factor matrix, a diagonal matrix, and the second factor matrix pseudo inverse. Okay, so what this means is that if we compute, well, after computing these two matrices, if we compute their eigendecompositions, that's going to recover the columns of A and the columns of B, provided that all of these entries are unique. And if all of these entries are unique, we can then pair up, essentially each entry of this matrix is the reciprocal of the corresponding entry to this matrix. So we can then pair up eigenvectors, i.e. the columns of A, with the columns of B correctly. The reason we can do this, again, this requires each of these entries to be distinct, but because we've assumed that every S by R submatrix of C has crystal rank at least 2, these linear combinations end up being distinct. These coefficients end up being distinct with probability 1. So this allows us to essentially not only recover the columns of A and B, but also pair them up in the right order. Okay, and so finally, the least square step. Once we know the first two factor matrices, we can find C by solving a linear system. So for each slice, we have the following system of equations. We have the sum over each of the rank 1 components of some entry of the first factor matrix times some entry of the second factor matrix times some entry of the third factor matrix equals the observed entry. And so now, again, we know the A's, we know the B's, we need to solve for C. So this is just a linear system, and this is just a linear equation in the R entries in the kth row of C. And so now we can just, so if we had all n squared equations, meaning we have all n squared entries, now we have an n squared by R system of equations. But we don't need all n squared of those. We only need a subset such that that system is a full rank. So what we can do is use a QR decomposition on that n squared by R matrix to then identify R indices, ij, such that the system is full rank. And once we do that, we just need those R samples in every slice. So that's N times R samples in total. And of course, when you add up the sample complexities, you get, I think, we go back. Yeah, if you add up this sample complexity with the N times R samples at the end, that's still dominated by this. So that's the final sample complexity. Okay, cool. So now what about non-adaptive sampling? So suppose we have, so we can still use the same idea. Let me actually just skip ahead to a picture. So we can still do the idea where we've sampled 2 slices very densely, and then the remaining samples sparsely. It's just that because we have to get all the samples first and then complete the tensor, we have to use slightly more samples. So suppose we construct our sample set by picking some subset of slices with some subset of S slices. And what we do is in the subset of S slices that we pick, we're going to sample them densely. So we're going to sample them with probability, some constant, the coherence, or log squared of n over n. And the remaining n minus S slices, we're going to sample those sparsely. So we're going to sample those with probability, some constant, coherence squared, r squared, log n over n squared. So typically this will be much smaller than this probability. Okay. So now when we do that, there exists a reconstruction algorithm such that for any CP rank R tensor whose factor matrices satisfy these conditions, the algorithm completes the tensor after observing this many entries with high probability. So note the number of entries is linear in n. But now we have like a log squared of n factor instead of a log of r factor. And in this term, we have like the coherence squared and r squared. But again, the important thing is that it's linear in it. And so the conditions are the same as before, except now we need the second factor matrix to also be full rank. Or sorry, the second factor matrix to also have a bounded coherence. Okay, so that is our non-adaptive sampling algorithm. And again, the proof sketch is very similar to this. We again complete S mode 3 slices via a non-adaptive sampling method. So essentially we use Chen's 2015 result, where we sample these with some probability and then use nuclear normalization. And that guarantees that we need something on the order of a coherence NR log squared of n samples for each of the S slices, which is where we get the S times coherence NR log squared of n part of our sample complexity. Then we use the simultaneous diagonalization algorithm on this completed n by s subtensor to learn the first 2 factor matrices. And then after learning the first 2 factor matrices for each mode 3 slice, we now have these random samples that we acquired at the beginning instead of after learning A and B, and solve that system of equations to learn a row of C. Using random matrix theory, we can show that with the coherence squared, r squared, log, and random samples per slice, that ensures that with high probability, each of the n systems of equations for learning a row of C is full rank. Also, I think I might have forgotten to mention this. This kind of looks like a sandwich, which is why we call this this sampling pattern. Kind of looks like a sandwich, which is why we called it a tensor sandwich. Okay, so yeah, so that's the results in the order. That was the order 3 case. So now let's go to the order D case. So with the order D, things are a little bit more complicated because we now have D modes instead of 3 modes, but otherwise things are kind of similar to the order 3 case. So for an order D tensor that's n by n by n by n all the way up to n, again, everything extends to general dimensions, but we're keeping this as a hypercube for simplicity. The CP decomposition is again a sum of rank 1 tensors. Again, we make factor matrices by taking the kth mode's factor vectors and stacking them into as columns of this matrix. Yeah, just for notation purposes. So again, in the non-adaptive and uniformly random sampling case, Stefan and Zhu obtained an n to the d/2 sample complexity. And for adaptive sampling, the method in Krishnamurthy and Singh's paper recovered the tensor with high probability and used something on the order of d squared coherence to the d-1th power n r to the d-1/2 power log of dr over delta samples. And they needed the first d-1 matrices to have a bounded coherence. Okay, and so now here are our results in that case. The intuition for these results are essentially the fact that if under mild conditions on the last several factor matrices, we can take subtensors of our order D tensor and then use our order 3 method on those tensors and then stitch those results together to get the CP decomposition for the order D tensor. So our theorem is that there exists an adaptive sampling and reconstruction algorithm such that for any order D tensor with CP rank R, whose factor matrices satisfied the first 2 factor matrices have to be full rank. The first factor matrix has to have a column space coherence bounded by some mu naught. Every S by R submatrix of the third factor matrix has to have critical rank at least 2. And the third through d factor matrices have no entries which are exactly 0. I'll come back to this point in a minute. Then the algorithm completes the tensor after observing on the order of S coherence n rank times log of R over delta plus D and R entries with probability at least 1 minus S delta. Okay. So this has a better dependence on the rank and the coherence than the previous Krishnamurthy and Singh result with slightly different conditions. Essentially like their result, if you saw, they had the coherence to the d-1th power and the rank to the d-1/2 power. For our result, it's just the coherence to the first power and the rank to the first power. The downside is like, for this simplified theorem, we assume that all the last d-2 factor matrices have no entries which are exactly 0. This is just so that every subtensor of that full tensor is full rank, and that means we can take any subtensor, perform our order 3 algorithm on that subtensor, and learn all our rank 1 components. But we can actually relax this condition by allowing each column of these factor matrices to have at most some factor like z times n entries, which are 0 for some numbers z in 0 to 1. Essentially, this requires a higher sample complexity because now we have to randomly sample several subtensors rather than just picking one. But it allows us to, and it makes the theorem slightly more complicated and harder to present on a single slide. But it's there and it's in our paper if you need it. Let's see. Is there a reason why the, so I have a question. Is there a reason why the bound on the critical rank of the S by our submatrices only applies to mode 3? Yeah, so essentially, yeah, okay, so I guess, so I guess technically what we do is we take several factor matrices that are, or sorry, we take several tensors that are along modes 1, 2, and 3 and have singleton dimensions on 4 through D. Take all of those subtensors to try to learn the first 2 factor matrices. But once we learn the first 2 factor matrices, then we can learn the third, fourth, etc. factor matrices using just solving linear systems of equations. So we no longer need this condition. Once this condition is only necessary for that simultaneous diagonalization step to work out. Does that answer your question, Ollie? Okay, great. Okay, cool. Yeah. So now for our non-adaptive sampling result. Again, for carefully chosen subsets, which we have in our paper, but again, would very complicate the presentation of this theorem. where we have one subset of size on the order of n squared and the other subset on the order of n cubed. We're going to construct our sampling set by including every entry in this dense subset. So some part of the tensor gets sampled with this probability coherence r log squared n over n. And the other part of the tensor gets sampled with probability coherence squared r squared log n over n squared. So once we've done that dense and sparse samplings of two regions of the tensor, then what we can do is say that there exists a reconstruction algorithm such that for any CP rank R tensor whose factor matrices satisfy these conditions, which are the same as before, but now the column space coherence of the second factor matrix is also bounded by mu naught. Then the algorithm completes T after observing this many entries with high probability. And so the number of entries is, again, note that it's linear in n and only has like a mild coherence square dependence and rank square dependent. So, and again, we can also relax this fourth condition by allowing each column of those factor matrices to have at most z times n zeros, but it would just increase the sample complexity. Okay. So now the question is, what about noisy data? So everything I've said previously applies to the noiseless case. But real world tensors have noise. And unfortunately, we don't have any like hard theoretical guarantees on what to do with noise. So one option, the default option, I guess, is just to throw it into our tensor sandwich algorithm and just hope that things get recovered. But that may not be the best. The other thing we can do is take the output, we can still throw it into our tensor sandwich algorithm and get something out. And then we can refine this algorithm using what's called alternating least squares. So alternating least squares is a reasonably popular way to recover the CP decomposition using either all the entries or even a partial set of entries. The idea is that we essentially, if we knew two of the factor matrices, then solving for the third factor matrix is just like a least squares problem, essentially. And what we can do is we can fix, let's say, factor matrices B and C, and then solve for the A that minimizes the sum of squared errors, so the total amount of noise that might have gotten added. So then we get a new A. Then we can fix A and C, and then solve for the B that gives us the least sum of squares of errors. And then we can fix A and B and solve for the C that gives us the minimum sum of squares of errors. And then just repeat this three-step procedure over and over. This has an interesting property that, like, if you start close enough to the true solution, then you get quadratic convergence to the true solution. But the catch is that you have to start close enough. If you start too far away, you either won't converge or you might even diverge. So you have to get a good initial guess before you can converge. And there are some heuristics on how to get a good initial guess, but they don't always work in practice. Okay, so this leads us to our experiment on synthetic data. So we're going to compare three tensor completion methods. One is that we just use alternating least squares on the factor matrices with, I think, one of the standard spectral initializations for these factor matrices as like as the starting point. Option 2 is the tensor sandwich algorithm, which is our adaptive sampling method for order 3. And option 3 is that we take our tensor sandwich algorithm and then perform ALS to refine it. And so what we see in this plot here is that when you have just alternating least squares, so our plot's comparing the relative error versus like the SNR of the noise. So this is the signal to noise ratio. So low SNR means a lot of noise, high SNR means very little noise. And so for ALS, just ALS by itself, we don't really get good convergence, even in the high SNR regime. So even when there's very little noise, this throws off ALS and we don't converge to anything close to the correct answer. Meanwhile, our tensor sandwich algorithm does get good convergence. So as the noise gets lower, we do get better and better reconstruction errors, which is what we'd expect. There is a limit though, because our tensor sandwich algorithm does have parts of this, the tensor sandwich algorithm that were made robust to noise do need several iterations, and that can running it for too many iterations can slow things down, which is why this graph doesn't keep going down essentially. But if we take our tensor sandwich output and refine it with ALS, we get even better convergence. So that shows that our tensor sandwich algorithm works, and we can even refine the result and get something better. Let's see, how many samples are we using? I am not 100% sure. I'll have to check with Cullen on that. We can probably do that like at the end of the talk. Okay. And so here's another experiment on hyperspectral imaging data. So this comes from the Indian Pines data set. Again, we have essentially this is some neighborhood, and we have several slices which correspond to different hyperspectral bits of information over the same region of space, over the same area. Essentially, we again compared alternating least squares, our tensor Delhi algorithm, and our tensor Delhi algorithm refined with alternating least squares. Again, we see the best performance by the tensor Delhi refined by alternating least squares. Again, better performance by just tensor Delhi than alternating least squares. Also, you can check visually that even like alternating least squares, even when you push up the estimated CP rank up to like 60, it still recovers something that's kind of a blur. Whereas the tensor Delhi algorithm and tensor Delhi algorithm with alternating least squares recover something that visually looks similar to the original image. So again, more so another, I guess, positive thing of our tensor Delhi algorithm. Yeah, and so again, this keep in mind in this data set, this is a real world data set. There's no guarantee that the thing was had low CP rank, but with like a CP rank 60 reconstruction, we were able to still get a reasonably good approximation. Okay, our paper also has simulations for order 4 and higher tensors, but for time constraints, I won't go over those. So regarding conclusions, so again, for completing an order D n by n by n by n tensor with CP rank R, our adaptive sampling approach uses order coherence NR log R plus DNR samples with high probability, which is a significant improvement over the adaptive sampling result, which used coherence to the D-1 and R to the D-1/2 log of D over R samples. And there was only a minor change to the assumptions. So again, we were able to improve the dependence on the coherence and the rank, and the slight tweaking on the assumptions. For our non-adaptive sampling approach, again, we had a slight change from using IID uniform random samples. We had to take IID uniform random samples over two different regions of the tensor with different probabilities, sampling probabilities in each of those regions. But with that approach, we were able to reduce the sample complexity from n to the d over 2, drastically down to something that's linear in n. And get something that works practically in a reasonable amount of time. For future work, again, we want to prove theoretical guarantees for noisy tensor completion. This is a challenging problem. This will likely require more assumptions on the tensor, such as the factor matrices have something either are orthogonal or close to orthogonal or something like that. Otherwise, there's lots of things that could trip us up, such as having rank 1 factors that nearly cancel each other out, and then having the noise perturb it such that it goes to a lower or higher CP potential. So it's challenging. No one's been able to do that so far, but we hope to be able, or at least in the case of CP rank, but we hope to be able to do that in the future. So again, thank you all for attending this talk, and thank you to the organizers for inviting me. Here are 2 papers and the codes available at these 2 links. And I guess I'll take any questions.
Great. Thank you very much for the talk, Santhosh. Does
Yeah.
anyone have any questions for our speaker?
Oh, and thanks to Cullen for answering one of the questions in the chat.
I have a question. My name is Alexander.
Hey, just to make sure, did we stop the recording for the questions or not?